Hello friends, so we will continue our derivation of radiative transfer equation. So in the previous lecture we discussed what are the basic mechanisms by which the radiative intensity can increase or decrease. So we will continue by adding all the components. So we have a ray of photons and this location is let us say S and this location is S plus ds. The time taken by the photon to reach from S to S plus ds is dt. This is the time required, although this time is going to be very less because the speed of radiation travel is the speed of light. When the radiation travels from S to S plus ds, its intensity will increase because of in-scattering. So, in-scattering is the amount of energy scattered into this direction. So, intensity will come from other directions and it will in-scatter. There will be some emission. The intensity will decrease because of absorption and out-scattering. We discussed all these facts. So, we add all the components. So, we write that intensity at S plus ds at time t plus dt in a given direction S cap. So, this direction is S cap minus intensity at point S at time t is basically the component from emission, augmentation by emission, absorption, attenuation by absorption, attenuation by out-scattering and augmentation by in-scattering. So, we see that the integration in this equation appears in the in-scattering term and phi lambda is the scattering phase function. Now, the difference between the intensity at S plus ds and at S we can write down using the differential calculus as dt partial I lambda by partial t plus ds partial I lambda by partial s. Now, substituting this for I lambda s plus ds minus I lambda s in this equation, we get the following equation. Okay. Now, this equation appears to be a partial differential equation because of the partial derivatives appearing on the left hand side, but this equation also appears to be an integral equation because of the integral appearing on the right hand side. So, this equation is basically called integral differential equation. So, in radiative heat exchange between plane surfaces you studied integral equation. This is one step further and more complicated, integral differential equation. Okay. So, it has 7 independent variables as we discussed in the previous lecture also, 3 space coordinates, 2 direction coordinates theta and psi, time and wavelength, and this is an integral differential equation. Now, unless and until we are dealing with lasers of the order of picosecond and femtosecond, where we may be interested in modeling the transient radiative heat transfer. So, in lasers with such a short duration pulse lasers, we may be of there may be of interest to deal with transient radiative heat transfer, because the time scale is so small that the radiation travel between 2 paths S plus ds in this short duration may actually be of consideration, but for other applications this transient term is not required and we can neglect it, and once we do that the equation what we call quasi steady form can be written as this equation, where partial derivative has now replaced with direct total derivative d I lambda over ds, because the dependence on time has been removed, and this equation again this is an integral differential equation. On the right hand side we have the emission, absorption, we have introduced the extinction coefficient beta lambda, which includes absorption by or attenuation by absorption and scattering also, the out scattering, and the last term is in scattering or augmentation by scattering. Often we non-dimensionalize this equation. This is called RTE or radiative transfer equation. So, this equation is called radiative transfer equation. We non-dimensionalize the radiative transfer equation by introducing the optical depth tau lambda. We have already defined it. We defined optical depth in terms of extinction coefficient. So, omega lambda is basically we define one more non-dimensional parameter omega lambda, which is basically the ratio of scattering coefficient and extinction coefficient. So, sigma s lambda is scattering coefficient and beta lambda is extinction coefficient, and the ratio is called single scattering albedo. Okay. So, this is basically a measure of scattering as a function of the extinction, and this parameter is called single scattering albedo. So, by introducing this parameter, the non-dimensional optical depth and non-dimensional single scattering albedo, we get the equation d I lambda by d tau lambda is equal to 1 minus omega lambda I b lambda, which is again the emission term, minus I lambda the absorption term, plus omega lambda upon 4 pi and the integral, which is in scattering term. So, this is non-dimensional form of the RTE. Now, boundary conditions for this equation. So, this is first order differential equation. So, we need to specify one boundary condition, and this boundary condition we can define for various type of surfaces we have already discussed, but we will just take a special case, that is diffusely emitting reflecting surfaces. So, the emittance of the surface may be epsilon. So, for this case the intensity leaving the surface I lambda it could be a function of wavelength, but here I am just writing it for the total. So, intensity leaving the wall is basically diffuse and can be written in terms of radiosity. So, this is the intensity leaving the wall. It has two components, the emission from the surface and reflection for the radiation coming on to this. Okay. So, this is emission and the diffuse reflection. So, this is reflection. Okay. Now, this H is irradiation, we have already discussed this. Irradiation is integrated on all the solid angles. So, we have used the vector notation on all the solid angles we have to integrate. Now, this radiation is coming from the gas or it may be coming from other surfaces. So, we have to include the effect of radiation coming from gas as well as other surfaces. So, again the boundary conditions is going to be integral equation. This is same as we have done for the heat transfer between surfaces. The boundary condition for this case is integral equation. The governing equation is integral differential equation and the boundary condition is an integral equation. For a black surface, the analysis is simple, and most of the problems that we will solve will assume that the surface is black. That means a medium is bounded by black surfaces, and the intensity, the boundary condition, the intensity is simply equal to the black body intensity. Here we are allowing that the intensity may vary over a surface. So, RW means the vector of any point on the wall. So, intensity may vary over a wall, but it does not vary in the direction. So, we are assuming diffuse surface. Now, once we have solved for the intensity, once we have the solution for radiative transfer equation for any problem, we can find out the quantities of our interest, and two quantities of interest in heat transfer community are the heat flux and divergence of heat flux. Heat flux is used to design surfaces for heat transfer equipments, be it boiler surface, be it the combustor surface, and divergence of heat flux is needed to know how much energy is absorbed at any location. This may be of interest in combustion application. So, we define heat flux as basically intensity dotted with the normal vector. So, we have a surface on which we want to find out heat flux. So, this is the intensity I lambda coming from certain direction S cap, okay, and this is the normal vector n cap. So, heat flux is basically the normal component of the intensity. So, we take a dot product of intensity and n dot S basically appears, and we have to integrate because intensity may come from all directions. So, we have to integrate over all the solid angles. So, the heat flux is basically defined as I n dot S cap, where n is the unit vector normal to the surface, S is the direction from which the intensity is falling on the surface, and we have to integrate over all the solid angles, and solid angles is going to be 2 pi if we are dealing with real surface, and it is going to be 4 pi if we are just trying to find out heat flux in any point suspended in space. If we have a space and we are interested in finding the heat flux at this point, then we have to integrate over the solid angle 4 pi because intensity will come from all the directions. But if you want to find out heat flux on a flat surface, then definitely the solid angle will be just 2 pi. The total radiative heat flux will then be calculated by integrating the spectral radiative heat flux over all the wavelengths. So, we integrate over the entire spectrum 0 to infinity, and this will give us the total heat flux. Now, divergence of radiative heat flux is needed in knowing how much total energy is emitted or absorbed at a given location in the medium. So, we take a small volume of element of volume dV, the size of this volume is dx, dy, dz. So, the total volume dV is equal to dx into dy into dz. The radiative energy enters this volume from 6 phases. Some amount of energy is absorbed within this volume and some amount of energy is emitted within this volume. So, we write an energy balance for this volume. So, radiative energy stored in dV per unit time, that is amount of energy, radiative energy change in this volume per unit time, minus radiative energy emitted plus radiative energy destroyed or absorbed by this volume should be equal to, so the left hand side is the total change in volume per unit time and the right hand side is the flux. So, flux of radiative energy at phase x minus flux of radiative energy at phase x plus dx, and same thing we have to do on the 6 phases. The right hand side can be simplified by solving for the q x plus dx, and we get del q by del x plus del q by del y plus del z by del q by del z dx dy dz, and this will be equal to simply del dot q dV. So, del dot q is the divergence of radiative heat flux. This is the divergence of radiative flux. We also call it radiative source term. So, this radiative source term often appears in the overall energy balance equation. So, if you have other modes of heat transfer, this radiative source term will appear as a source term in the overall energy balance equation. Now, to solve for the left hand side, we take the radiative transfer equation and we integrate over all the solid angles. So, this is the radiative transfer equation. We integrate over all solid angles 4 pi, both left hand side and right hand side we do. Then we do little mathematical manipulation. We take the divergence operator outside this integral, and we define this integral over 4 pi I lambda s d omega, and same thing we do on the other terms. So, without going into much of the mathematical manipulation, here we will introduce one quantity which we call incident radiation G. So, incident radiation G is defined as basically the intensity coming from certain direction integrated over omega. So, this G is basically different from flux, and the flux is always measured normal to a surface. So, if we have to calculate the heat flux, we will take I lambda and the dot product between the surface normal and the direction SI, but incident radiation is defined as the total intensity coming from 4 pi direction. So, it is basically a measure of total intensity coming from all directions. So, we integrate the intensity from all the directions to get the incident radiation. So, simplifying the this equation, in terms of G, we get the first term, the emission term is 4 pi kappa lambda IB lambda, and this is the absorption term and this is the scattering term. So, we can simplify this and we get basically the divergence of heat flux is equal to kappa 4 pi IB minus G. Okay. This is valid for spectral basis also and this is valid for total basis also. So, this is the equation for radiative heat flux for on a spectral basis, and this is the equation for the radiative heat source term on overall basis. It could be valid on a gray basis also. So, we will do one problem, and this problem will clarify most of the concepts that we have learned so far on the equation of radiative transfer. So, what we have in this problem is basically a sphere. So, there is a sphere, the radius of this sphere is r, the sphere is filled with some gas with absorption coefficient kappa lambda. Okay. Outside the sphere is vacuum, okay, and the temperature is almost close to 0. So, vacuum and 0 temperature outside the sphere is specified because we want to exclude any external irradiation. So, we have this sphere which is filled with the gas, the absorption coefficient is kappa lambda, the temperature of the gas is uniform, kappa lambda is uniform, the temperature is T, the radius is r. Now, we have to find out the intensity of radiation coming out of this sphere I lambda. We have to find out total heat loss from this sphere, and we have to find out the divergence, the radiative heat source term at the center of this sphere as well as at the surface of this sphere. Now, this problem looks pretty simple as such, but as we will see that the mathematics even for this simple case is not that easy. So, now what we basically have to observe, so some observations we have to basically do first. So, the first observation here is that the intensity is not isotropic. Okay. That means intensity on this surface is not going to be same, it is going to depend on theta. Okay. So, intensity is going to be different at different angles, and that will depend on the polar angle. That is the first observation. The second observation is I is not a function of azimuthal angle. Okay. So, it will depend on theta, but it will be uniform in azimuthal angle. Okay. And then we have to basically solve for this problem. So, let us see how to solve this problem. We will the third assumption is that sigma s lambda is 0. So, there is no scattering, the gas is purely absorbing and emitting, there is no scattering. So, let us solve this problem. So, first of all we write down the governing equation of radiative heat transfer. So, d I lambda in non-dimensional form, d tau lambda is equal to 1 minus omega lambda I b lambda minus I lambda plus omega lambda upon 4 pi I lambda scattering phase function phi lambda d omega. So, this is the governing equation, the integral differential equation. Now, based on the assumption that scattering is not there, we have omega lambda is equal to 0. Okay. So, you just observe how we are simplifying the problem, and still the problem the mathematics of the problem is involved. So, this term will be equal to 0. Okay. So, our equation now reduces to d I lambda by d tau lambda is equal to minus or simply IB lambda minus I lambda. So, very simple differential equation. Okay. Now, let us look at it. This is in a given direction. Okay. So, we draw our sphere again. So, we are looking at the intensity at this point. So, this is our intensity I lambda in a given direction, let us call this S cap. Now, where this intensity is coming from? This intensity is coming from this part of the sphere, this is the center of the sphere. Okay. So, radiation along this path we have to calculate, this is the path. Okay. So, it may start at this point and it may go all the way up to this point on the sphere surface. Okay. So, this angle may be specified as theta. Okay. Now, what we will do is we introduce the coordinates along this direction. So, let me draw this one. This is S is equal to 0 and this is S is equal to 2 times tau r cos theta. This path, non-dimensional path I am talking. So, this is going to be 2 times tau r cos theta. Okay. This is r, this distance is r cos theta. So, this will become 2 r cos theta and we have multiplied by absorption coefficient to define the path. This is tau s, that means the optical path at the surface is equal to 2 tau r cos theta. So, we write this now I lambda, which is function of now tau r and theta, is equal to, we integrate it 0 to tau s IB lambda tau s prime e power minus tau s minus tau s prime and d tau s prime, where tau s prime is a variable along this path. Okay. So, tau s prime is simply s ds prime times the absorption coefficient kappa lambda. Okay. So, we have to integrate this. So, this is the solution for this this path I lambda, which is function of tau r and theta, and is equal to 0 to tau s IB lambda tau s prime exponential minus tau s prime, where tau s is nothing but 2 tau r cos theta. So, tau s is measured in this direction, while tau r is simply, tau r is nothing but kappa lambda times r. Okay. So, now we will write this as I b lambda, IB lambda as a function of tau s prime. Now, IB lambda does not depend on path. Okay. Black body intensity is isotropic. So, IB lambda is simply a function of temperature only. Okay. It does not depend on path. So, we can take it out of the integral. So, our I lambda then, which is function of now tau r and theta, is equal to IB lambda taken out 0 to tau s exponential tau s minus tau s prime d tau s prime, and this will be equal to IB lambda e power minus 2 tau r cos theta minus tau s prime, and then this will be 0 to 2 tau r cos theta, where we have substituted tau s is equal to 2 tau r cos theta. Okay. Now, we just finalize the solution by putting the limits. So, I lambda tau r theta. So, I lambda is a function of tau r and theta is equal to IB lambda, which is function of temperature only, 1 minus e power minus 2 tau r cos theta. Okay. So, this is the equation, this is the solution for intensity. Okay. And as is clear, intensity is a function of theta. Okay. So, for a sphere, the intensity will be different in different direction. Okay, it will be different in different directions. Okay, so at any point on the surface of the sphere, the intensity is going to be different in different directions, is a function of theta. Okay, for tau r greater than 1, that means we have a large sphere or optically thick. Optically thick means we have kappa lambda as large, that means we have strong absorption. Kappa lambda large means we have significant absorption. Kappa lambda or tau lambda greater than very large than 1, it is optically thick. In that case, the exponential term will be equal to 0, and I lambda tau r theta will be simply equal to I lambda. It will not depend on tau r and theta, and it will be simply equal to I b lambda. Okay. So, for optically thick spheres or any medium, it applies to any medium. It could be sphere, it could be rectangle, it could be cube. Okay. So, for any medium, optically thick medium, the intensity does not depend on direction and it does not depend on the absorption coefficient. Okay. So, it is independent of kappa as well as theta, and the intensity is simply equal to the black body intensity, and that is what basically we have in case of sun. So, sun is a very large sphere and the intensity coming out of the sun is black body intensity, equal to black body intensity, and we have basically proved why sun behaves like a black body. Now, the second part of the problem, the total heat loss. So, total heat loss is basically the total amount of heat flux over the surface at any point. Okay. So, total heat loss is equal to 0 to infinity q lambda at any point. So, q lambda tau r, we dot it with the normal vector. So, we have this sphere, this is the local normal n cap. So, we have to find out the heat flux q lambda dotted with the local normal and integrating over the entire wavelength region. So, we get 0 to infinity I lambda and again integrating over 4 pi. So, I lambda, which is a function of tau r and theta, n dot and s cap d omega. Okay. So, intensity is a function of theta. So, we have to take a dot product with the normal vector to calculate the heat flux, and that heat flux will be spectral heat flux. We have to integrate over the all the wavelengths. Okay. So, this will be equal to 0 to infinity 0 to 2 pi I lambda tau r theta cos theta for n dot s cap, and d omega becomes sin theta d theta d psi. Now, there is no dependence on psi, so we can solve for the psi first, and this will become 2 pi 0 to infinity 0 to pi by 2. So, we get I b lambda. So, substituting the expression for I lambda, this expression we put I b lambda 1 minus e power minus 2 tau r cos theta sin theta d theta and d lambda. Okay. So, total heat loss, that is basically the heat flux per unit area at any location on the surface of the sphere, can be written then as 2 pi integration from 0 to infinity integration from 0 to pi by 2. So, we have splitted the solid angle into azimuthal and polar angle, and this will be equal to I b lambda 1 minus e power minus 2 tau r cos theta. This is the variation of intensity with respect to theta. So, we have substituted the value of intensity cos theta sin theta d theta and d lambda. Now, in this expression the Planck black body function IB lambda is independent of theta. So, we can just pull it out, and this will be equal to now pi times IB 1 minus 1 over 2 tau r square 1 minus 1 plus 2 tau r e power minus 2 tau r. Okay, so, this is the expression for the total heat loss. Pi IB is simply sigma T power 4, the black body emissive power. So, 1 minus 1 upon 2 tau r square 1 minus 1 plus 2 tau r e power minus 2 tau r. So, this is the total heat loss from the surface of the sphere at any location on the sphere. This is per unit area. If you want to apply the total heat loss, we have to multiply by the surface of the sphere. Now, the other quantity of interest is basically the divergence of heat flux. We have to find out divergence of heat flux at the two locations. So, the divergence of heat flux is defined as del dot q is equal to 4 pi kappa. Now, this could be spectral or it could be total, 4 pi kappa lambda IB lambda minus kappa lambda G lambda. Okay. Now, here we just assume that kappa lambda is equal to kappa, that means the gas is gray, the absorption coefficient does not depend on the wavelength. Okay. So, with this first we evaluate G lambda, which is equal to intensity at a given direction integrated over all the solid angles. Okay. So, we will have we can write d omega as sin theta d theta d psi and then integrate over the solid angle. So, this will be equal to 2 pi IB lambda 1 minus e power minus 2 tau r cos theta, that is the intensity sin theta d theta, and we have to integrate from 0 to pi by 2. So, this will once we simplify this, we get pi times IB lambda upon tau r. Okay. So, tau r although is a function of wavelength, but we have assumed it to be gray. So, I will just write it as tau r, and this will be equal to 2 times tau r minus 1 plus e power minus 2 tau r. So, this is the radiative intensity. So, del dot q is simply equal to 4 pi kappa lambda IB lambda minus kappa lambda G lambda. So, we substitute the value of G lambda here and we get sigma T and integrate over all the wavelengths d lambda. So, we also integrate over all the wavelengths d lambda. So, this will be equal to sigma T power 4 by tau r 2 tau r plus 1 minus e power minus 2 tau r. Okay. So, this is the expression for the radiative heat source term integrated over the entire spectrum at any location on the surface of the sphere. Now, at the center of the sphere, we have intensity I lambda. From the expression of the intensity is equal to IB lambda 1 minus e power minus 2 tau r. So, this is the magnitude of intensity of radiation at the center of the sphere, and this is going to be isotropic. Okay, it will not depend on theta. So, G lambda at the center is simply equal to 4 pi IB lambda 1 minus e to the power minus 2 tau r, and del dot q will be simply equal to 4 kappa sigma t power 4 e power minus 2 tau r. So, this is the del dot q at the center and this is del dot q at the surface. So, in this lecture we have seen how to apply the equation of radiative transfer to some special problems, one dimensional problems where we have a sphere, and gray problems where the absorption coefficient was not a function of wavelength, and we did lot of simplification and solved for important parameters like heat flux at the surface and del dot q. We will apply in subsequent lectures the same techniques to solve radiative heat transfer in cylindrical and plane parallel geometry. So, I thank you for your kind attention. We will continue in the next lecture for some special cases of radiative transfer, one dimensional cases. Thank you.